This video updates information on slide 18 of the original video, which is the Schwarzschild's geodesics video number 3, concerning the condition for stability of a circular orbit in the Schwarzschild geometry. Now, this is updating, it's not a correction, it's a clarification. I want to provide a little bit of extra detail to make the point clear. I think there was a point on slide 18 which I haven't made clear enough, and so I want to update that. What I'm going to do is start 2 slides earlier. I'm going to go back at slide 16 and go forward from there. Okay, so we had the effective potential. Now, circular orbits occur. This is slide 16. Circular orbits occur when the derivative of the effective potential with respect to radial coordinate is 0. That derivative is this one here, this object here. The algebra for all this was covered in the previous slides on that video. And now we set that equal to 0 in order to determine the location of the circular orbits. This gives us 2 solutions. One is the Schwarzschild event horizon itself. Clearly you can't have a circular orbit there. A particle reaching that surface crosses it and then continues on into the singularity. So no stable circular orbits are possible there. The next location is this one here, and this will turn out to be both stable, where the innermost stable circular orbit is possible. So only the second solution is viable because any particle at the first radius must continue on into the singularity at the center, and so cannot exist in a stable circular orbit. Now, to check the second solution for stability, we use the second derivative. And it's this bit here I will get to. So the second derivative is this object in here, carried out here. I'm not going to go through all the steps, but you can check for yourself and you see that you get this. Now, the condition for stability is that the second derivative with respect to the radius is 0. What you'll actually find in practice is that you'll get a quantity like this. Now, for Schwarzschild black holes, given the mass of the black holes, given the small value g, you square that. What will happen is that you'll end up getting something very close to 0. So if you've got a 10 billion solar mass black hole, then this quantity here is roughly of the order of 10 to the minus 10. So it's negligibly small, very negligible. So it's approximately 0. And because it's not exactly 0, we have to talk in terms of marginal stability. But when dealing with black holes, whether it's the Schwarzschild one or the Kerr one later on, you're going to find that this quantity is so small that it's effectively approximately 0. And so what that's telling us is that at r equals 3 times the Schwarzschild radius, we really have a stable minimum. The innermost stable circular orbit occurs at that value, 3rs, which is 6gm on c squared. It's marginally stable because this quantity is not exactly 0. This is true, it's greater than 0, but it's very, very close to 0. If you start plugging values for m for different black holes, you're going to find that this is really very small, negligible. Okay, so I can't say exactly 0, but we'll put approximately 0 there. Okay, this slightly positive, almost 0 second derivative at the point in question is in fact the condition for marginal stability of circular orbits. We'd be able to completely say with confidence stability if that was exactly 0, but it's not quite. It's very, very close, so we say marginally stable. Okay, and that was that's the update, that's the clarification here. Okay, so effectively this is approximate 0. The second derivative equal to 0 gives us stability. This is almost 0, so it's marginal stability.